Hello everyone, welcome to another episode of Reconstructing the Game of Go, written by John Millen, as it has been presented in a Byte magazine in April 1981. So today we have a routine to handle user input. And quite interestingly, this video is sort of a milestone because until now I could run this code in my recent Linux emulator of a KIM-1, but from now on I can no longer do so. And the reason for that is because of the original implementation of the program. So I really want to stick to the original implementation, and hence this kind of decision. So what's the problem? The idea is that here on the picture you can see how the KIM-1 computer looks like. So it has a keypad and the 7 segment LEDs here. And here I have a serial monitor. It's not active now, it would be showing the board. You can essentially go to the serial mode and try to enter your program from the serial mode. And this is exactly what we have been witnessing within the KIM-1 emulator for Linux. But the problem is the user input. So the way the original program did handle the user input was the following. It assumed the user is pressing the keys on the keypad to enter the move where he wants to place his stone. And the best move that computer responds with would be rendered on the screen. Meanwhile, the board would be printed to the serial monitor. So the problem is that we are not taking the move while being in a serial mode, and this program is not working in a serial mode. It does output the board to the serial port, but it's not like working in the serial mode. And to be very honest, before I read that in that article, I didn't really think this is technically possible. But I don't know, maybe that was some sort of a hack, or I don't really know. And this very version provides the exact behavior that has been described in the Byte magazine by Jonathan K. Millen. So, um, let's probably go into the source code because the way how the user input is being handled is very specific to how Keypad works on KIM-1, and understanding how Keypad works is essential to understand how the entire user input routine is working. So the addresses are continuing from the previous part, and the last function to put bulk coordinates into the 0 page ended up with 0258 with a return statement. And starting from there, we start the new chunk of code. So I store the variable called user move at the location 0259 hexadecimal. And yeah, it's arguable where to store variables, so maybe I should move all the variables to the very end of the page or somewhere else. But since I ran out of available locations in the 0 page because it's entirely occupied by the board square notation and the board itself, I decided that probably I can put the variable that I need within a certain function just right above the function. So the user input routine starts here at 025A, and we do the following. So there is a KIM-ROM routine called getKey, yeah, and getKey gets the value of the key that is now being pressed, and it stores the value of that key into the A register. But the idea is that it only stores the value to the A register when the key is pressed. So say I press and hold 9. So by the time I hold this 9, the value of the A register is going to be equal to hexadecimal 9. So it gets converted from the key code to the actual value. But if I release the button, then the value in the A register would be equal to 15, because that's the value used to indicate that there is no key being pressed on a keypad. So, with this kind of behavior, we are facing a bit of a challenge. I will now try to describe this in a bit more details. But before that, what we need to do is to shift 4 bits to the left to store the high bit of the byte, the most significant nibble of the bit. And we store this to the location of the user move over in here. Okay. Then, in order to listen to the second key press, if we just do this like repeating this exact code, so you might be wondering why I didn't put this into a separate function. The reason for that is the following. So if I do this, then the value in the A register would still be what I've already pressed. And the time taken to execute this code is so miserable that I would not be capable of physically pressing the button that fast, not even pressing, but releasing the button that fast. So next step we need to verify. We need to make sure that the keypad reaches the state where no key is being pressed. So I do the jump to the get key one more time, and this time I'm comparing the value of the A register with the 15. And this is the way how I can say that, okay, so the user has released the button. And once that has happened, we can move further on. So before user did not release the button, we would not try to execute the following code. We would just stuck over in here, and we're stuck in a loop. So we're going from here to here until user releases the button. Once that has happened, we can call this function again. So essentially we do exactly the same action one more time. So clearing the carry flag and asking what key has been pressed, and if the key is greater than F, and we use 0 because of the nature of how the carry flag is being set. So it might also have the value of 13 sometimes, maybe because that's the value for the go button, I'm not quite sure. Anyway, so we're only interested in listening to these buttons because these buttons are not used in the program. Okay, so once we got another button click from the user, we have just stored the least significant 4 bits, the least significant nibble, into the A register. And once we have that, we need to bitwise or whatever we currently have in A register with the most significant nibble that is being stored in the user move, okay, which is the absolute address. So after this, we already have the square where we should put the stone, and it's stored in the A register. So all we need to do is to overwrite the user move location with a newly updated value. After that, we have a square where to place the stone being stored in the user move. So we're loading that value into the X register. And then we're loading the value of full F, which is the uppercase O, which represents the white stone. So user is always playing white in this program. So we load this value to the emulator and storing to the board indexed by X. We have a stone being placed on board. And we don't need to perform any additional calculations because the value that user has entered is exactly the coordinate. So say this is like 3, 3, and this means that at the memory cell 33 we need to place a stone. So the first digit represents the row and the second digit represents the column. Okay, and finally, just to have a little driver program to make it working, because you remember that in the 0 page, starting from the value of EF and up to the FF, KIM-1 is using those cells for its work, so it outputs some data there. And by the time program is working, we need to make sure that that is not the case, because otherwise the board position would be messed up. So we really want to make sure that we do put in stones and all the possible operations within the loop, within the game loop, essentially. So to provide that, we have this one. I did not specify the addresses here yet because I don't know for now where exactly the program start would be and where the program loop would be. At the moment, it's located at 300 hexadecimal, but it will probably be moved further because yeah, I would need that space for other routines. Okay, so program start, which we're just clearing the decimal flag to make sure that the ADC add with carry and SBC subtract with carry instructions would be working properly without assuming binary coded decimals, but just in normal hexadecimal mode. And also, here is the main routine kind of. So we do the I/O here, input output. So we print the board, and then we call the user input, and after we just jump back to the program loop. With this two function calls, what we achieve is we print the board and Keypad is waiting for the user input. So every time I can input some values, and every time I click two buttons, the board position would be updated with a newly placed stone. And now comes the final update. So I already have a paper tape prepared to show you how this program is going to be working. So all the bytes, not only from today's video, but from previous videos, are all going to be put into memory. But the update regards the emulator itself. So it now can directly import the paper tape and export the paper tape. Importing is what I'm going to be using now, and exporting, let's say you made some work, you want to save your work, you can export paper tape. Previously, since all the codes were in 6.502 assembly, and the previous version, like not the previous version, but another version, initial version did have the assembler and disassembler, and the code was meant to be stored in a text file somewhere and being pasted, like assembly source code was meant to be pasted into the text area and uploaded. But this is the old school version, so here we only interact via paper tapes. Anyway, so I click import paper tape, and it automatically finds where the code should be loaded, because the starting address is available within the paper tape itself. So if you have a look here, so we have the address of 0200 where we start uploading. This does not necessarily mean that the program would start at 0200. This needs to be additionally fetched from a README or something. So in my case, in this particular case, the program would start at 0300, hexadecimal 300s, starting with the clearing decimal flag, and then go into the loop that I have described. So I hold my breath and I click go, and I have this nice board being printed. So nothing new so far. You've seen this in the previous video, so nothing new so far. But say I want to place the stone over in here. Okay, okay, I just entered the serial mode. I should not click. Okay, I should not click. So let's try one more time. Yeah, if I click on it, I'm in the serial mode. If I click again, I go back to the keypad mode. So I should be in the keypad mode. Yeah, I go to 0300 and go. So say I want to put the stone here 3 3. So first specifying the row, then the column, and I say 3 and then 3, and I have the stone being placed on board. Since the user is only meant to be playing white stones, if I do this one more time, another white stone will be placed. But when I would add the logic to play the moves on the computer behalf, in that case, some black stones would be appearing in response to me placing the white stone. Also, there would be some handicap stones, just like in the original program. But for now, let's put the stone to say C4. Okay, so C and 4, and I place the stone here. Let's put the stone to D3, for instance. No, D3 is this one. No, hold on a sec. D3 is this one. D3 is D3 is this one. This one is 3D. So 3 and D. Okay, and let's put the stone say here. So this is going to be B B, yes, let's put here B, C. So B and C. And we got stone here, B, C. And I feel so proud about this, guys, really. This is the exact behavior of how the original program has been described in that article in the Byte magazine. So just user clicks on keypad and the board gets printed in the serial monitor. And also there should be the best move by the computer being printed in the 7-second LEDs, but this is about to be implemented in future. But for now, yeah, just for the debugging purposes, this is fairly enough to have this nice board. And the next big milestone is to provide the count routine, the heart of the entire program. I thought I would be providing count in this video, but I realized that without having these IO loop, it would not be possible to debug count properly. So I would need to put the call to the count into the main loop to make sure that the connected groups would be marked properly and the liberties would be counted properly. And then it comes to removing stones if user captures the group, or remove the stones if computer captures the groups, and so on and so on. Then the program logic as well. All this is hard coded. All the move priorities are hard coded as the order of operations to have, and all that is described in the article. So yeah, I will probably take a note on that and show you some pseudocode by Johnson Camille. I did this before when I was trying to port that program to Python. Not exactly porting, but trying to make my own Goblin program in Python. Back in the day, I've been doing some tutorials on that. But that was not even close to what I'm doing today, because this time I'm trying to make a program as close to original as possible. So hey guys, this is it from my side. I hope you enjoyed the video, and I'll see you in the next one. Until then, and cheers.